Hello mathematicians, we're now going to have a little look at rates of change. Now in the long run this is a really important concept and it's really where calculus interfaces with the real world. So we'll be doing rates of change of populations, of radioactive materials, of speeds, accelerations, different sorts of motion and so on. So it's as I said, the interface in a sense between maths and physics. And it's all based on the fact that while we've talked about the derivative and it's been focused for us so far on slopes, we have to remember that a slope is really just a rate of change of y with respect to x. Because that's what gradient is. Change in y, y2 minus y1 over change in x, x2 minus x1. But the thing is that we can apply the techniques of differentiation to a rate of change between any two variables. So if we thought about, for example, the rate at which you covered distance, then we know that that is velocity. So as we'll see later on, velocity is actually the differential of distance with respect to time. However, we're going to have a little dabble here for a case where two variables are in turn related to a third variable, which often happens to be time in the real world, and the rule that we're going to use most often is the chain rule. So what we end up doing is try to express one quantity as a function of the other quantity, then differentiate with respect to time using the chain rule. Units are often a clue as to how things relate, and really the best way to learn these is to do them, think about them, and test them against your common sense. So this is essentially extension 1 work. 2-unit do rates of change, but not using the chain rule in the way that we will. So with these we're looking for connections. So we have a circular oil stain of radius r and area a. Now we know that there's a connection between a and r, which is that if it's a circle, the area of the circle is pi r squared. It then says differentiate the area formula with respect to time to show that dA dt equals 2 pi r dr dt. So where did that come from? Well, the thing is that if we think about the circular oil stain spreading on the water, that means that the radius is increasing as time passes, and that's why the area increases. So if we have a connection between the radius and the area, between the radius and time, and therefore between the area and the time. So if we write down that we want dA dt, how the area changes with respect to time, then it's going to be a chain rule. And as I said, this target, the thing that we want, how the area changes as a function of time, gives us a little bit of a clue about how to set it up. So we've got to have a dA on the top somewhere and a dt down the bottom, and we connect our other variables. So what does a depend on? We saw that a depends on r. So we can find that. We can find dA dr. If I multiply it by something where I can get a t on the bottom, and I don't want r to turn up anywhere, then that is the r dt. I want to see how the radius varies as a function of time. So when I go to do this differential, I can find dA dr. So if a is pi r squared, when I find dA dr, that is going to be 2 pi r. And I don't know anything about dr dt. I don't know I haven't got an equation for how r depends on t. I don't know the rate at which the radius varies with time. So this is my connection that I've got to work with. And in part A it says, find the rate of increase of area, so that is dA dt, that's the rate at which the area increases with respect to time, when r equals 40, so we can see that dA dt has an r equals 40 in it, if the radius is increasing at 3 centimetres per second. So 3 centimetres per second is the radius changing as a result of time. So 3 centimetres per second is dr dt. So therefore dA dt simply becomes 2 pi r where r is 40, multiplied by 3 centimetres per second. So that's going to turn out to be, what's that, 240 pi. And what do we measure that in? Because we're talking real stuff now. Well, what's area measured in? Square centimetres. And time is measured in seconds. So it's square centimetres per second. Now for part B, find the rate of increase of the radius when r is 60 if the area is increasing at 10 centimetres squared per second. So again, with this relationship here, what we're given now is dA dt. That's 10 square centimetres per second, which, not that it matters much, but we could think about as having a 1 second there. That equals 2 pi r, so r is 60, 2 pi times 60 times dr dt. So now it's just like any fraction sum, essentially. So dr dt, the rate at which the area is increasing, is going to be 10 divided by 2 pi times 60, so 10 over 2 pi times 60, which is going to be 1 on 12 pi. And what units will that be? That will be centimetres per second. Units of radius divided by the units of time. Now for our next question, again, read it carefully to get a feel for what's going on. So we have this spherical balloon, so we need to think about our formulas for a balloon. So we've got volume of the sphere, 4/3 pi r cubed, and that depends obviously on r, so there's a connection between v and r, and as r gets bigger, then the volume gets bigger. Why does r get bigger? Because we're putting water into the balloon, and the water is flowing in at 50 cubic centimetres per second. Now, what is that rate there? Well, it's talking about a volume, cubic centimetres, and a time. So this is really change in volume over change in time. It has this value of 50 cubic centimetres per second. The volume of the sphere, because it's getting added to, is going to end up varying the radius because of this connection. So we know that dV dr we can work out, so that will simply be 4 pi r squared. You might recognise that as the surface area of a balloon, a sphere. And then we think about what we're asked. So at what rate is the radius increasing? So that will be dr dt when the radius is 7. So now our task is to write the equation as a result of the chain rule. So if we want dr dt, how can we make that up from what we've got? Well, we can see over here that we've got dv dr, so if I wrote that upside down as dr dv, and we can see up here we've got dv dt, so if I wrote that like that, then you can see the v's would cancel out and we would just have dr dt. So then I simply plug stuff into it. So dr dt is going to be dr dv, so that's 1 on 4 pi r squared, and r is 7, so it's 1 on 4 pi 7 squared, times dv dt, which is 50. So then I'd simply work on simplifying this expression here, and plug that into the calculator, and without evaluating the pi, so using fraction keys, I get 25 on 98 pi. What will the units of this be? Well, it's units of radius divided by units of time, so it's centimetres per second. Part B, at what rate is the radius increasing? So again, dr dt when the volume is that thing there. So I want dr dt, and I notice that my equations will be as before. So I haven't got one which just has for when the volume is 4,500. So I've got dv dt, but not just for volume, except for this one here. Now when I know the volume, I know the radius, and therefore I can work with this. So when V equals 4500 pi, what does R equal? Well, from our equation then, R is going to be 3V on 4, so 3 times 4500 pi on 4 divided by pi, so the pi's go, and then the cube root of that number there, which we're very happy works out to be a nice number because it's usually an indication we're on the right track. So the problem is now, just like the first one, we want to find dr dt basically when r equals 15. So that will become 1 on 4 pi times 15 squared times 50, which will equal pi on 18 centimeters per second. And part C, what should the flow rate be changed to? I'm sure that should have said to what should the flow rate be changed, so that when the radius is 7, it is increasing at 1 centimeter per second. So again, we need to get our head around the language. So what is the flow rate? The flow rate is dV dt. What value of dV dt do we need so that when the radius is 7, it, presumably being the radius, is increasing at 1 centimeter per second? So if we were in doubt about it being the radius, think about the units. It's the units of distance divided by time, so that is dr dt. So again, it's our same relationship, and we want dr dt to be 1 centimeter per second. We want to change the flow rate, so that dV dt is what we want to find, and we have dr dV to be 1 on 4 pi times, and it said the radius is 7. So therefore, dV dt, our flow rate, is going to be 4 pi times 7 squared, which equals 196 pi, and again the unit, cubic centimeters per second. So have a go at these. Remember that this is our first taster of this chain rule. We do more of it later on, but the key is reading, thinking, maybe even recognising that you can treat these as fractions that cancel out. So have a crack.